Welcome back. Our next speaker is Professor M.S. Raghunathan, and he's going to speak on Ratner's theorem.
Thank you. Well, let me begin by extending my best wishes to Dani. Perhaps more appropriately, in the present Hindu atmosphere, I must give him my blessings as his guru. That would be more appropriate. Or let me also extend it to Jyotsna. Anyway, well, I must begin by some kind of an apology for the title and abstract I've given. It doesn't represent correctly what I'm going to say. Firstly, I don't really have a new proof of Ratner's theorem in its full extent. What I have is a proof in a kind of special case, which uses representation theory. And it is my hope that these ideas can really be pushed to cover Ratner's theory in general. But at the present point, I do not have a proof for the general theorem in any case. The special case I will be interested in is the case when I'm looking at a G mod gamma, which is compact. That is the only situation where I'm handling it. And that's not the only restriction. I also to make restriction of the kind of unipotent group I'm looking at. As we go along, I'll tell you what exactly the kind of restriction I have. But I'm kind of optimistic that this method will work, in the more general context. But I'm probably too old to really push it, and it's for younger people. And it's my prerogative as an old man to say some younger person should try it. That's whether they take it up or not. It's their will. Okay, let me begin by stating something. Okay, so G will be a semi-simple group and gamma discrete subgroup. Such that G mod gamma is compact. Incidentally, Ratner's theorem, which she called my conjecture, that conjecture was actually got to be known by people only because of Dani. Dani put it down in a paper of his, calling it Raghunathan's conjecture. And then he also created a modified version, which is what really works for Ratner's proof. It's a modified version that she proves, and then she deduces for her. Unfortunately, she called that also Raghunathan's measure conjecture, which is not true. Everybody knows that now, fortunately. It's an important modification which Dani made for the conjecture. I mean, but for some reason, Marina insisted on calling it Raghunathan's measure conjecture. It's appropriately Dani's conjecture. Should have been. Anyway, so I start with G semi-simple gamma discrete subgroup such that G mod gamma is compact. This condition, of course, is irrelevant for Ratner's theorem. She doesn't need that. She looks at any space G mod gamma and then looks at a finite measure on G mod gamma. That's the way she goes about it. Okay. Anyway, and let U be a unipotent, connected unipotent subgroup. G. The theorem of Ratner, as you all know, let me nevertheless state it, says the following. If mu is a U invariant ergodic finite. Oh, since I've assumed G mod gamma compact, this is not relevant, but in her, she doesn't make the assumption that G mod gamma is compact. U invariant ergodic finite measure. Let mu b invariant ergodic measure on G mod gamma. Then there exists H closed subgroup of G with H gamma closed. Oh, sorry. Subgroup of G and X in G mod gamma such that X inverse Hx gamma is closed G and mu is the Haar measure on Hx gamma by gamma. That is the theorem of Ratner. And what I arrived at this conjecture essentially because of Dani's work. He first proved that this statement is true for Horner cycles. That was one of the things that made me think of the conjecture. And there was also the other factor that led me to the conjecture is Margulis' theorem about orbit of a one-parameter group. Never keeps coming back to that kind of stuff. That's the kind of thing which. My original idea was that one proves it for Horner cycles. Dani had already proved for Horner cycles, and then do a downward induction for smaller and smaller important groups. This was my plan, so to speak, which didn't work for a long time. And once Ratner proved the theorem, of course, I was no longer keen on going back to the proof, but nevertheless, it was always haunting me a little bit. Okay? And the first thing I did was to first try to prove Dani's theorem about Horner cycles by other methods. And the method I wanted to adopt was representation theory. And when I apply representation theory, if G mod gamma is compact, you can look at the action of G on L2 of G mod gamma, and that decomposes into a discrete sum of representations. And therefore, it becomes a little easier to handle. So, as I said, I'm making this assumption. So, my first step was to prove Ratner's theorem, or rather, theorem for unipotent radicals of parabolic groups, which are parabolic subgroups of G. So my first efforts were spent on that. I could prove it in the case of compact quotient. And in fact, I remember telling Dani that I can prove in the compact quotient, but compact quotient is not that difficult, was what was Dani's reaction. Nevertheless, my hope was that what I did for Horner cycles can be done more generally by some kind of downward induction, which didn't work. Incidentally, the method which I'll outline actually can also be pushed through in the non-compact case. There are some technical difficulties, but they can be overcome for Horner cycles. So what I'm going to do is to now give you a proof in the case of Horner cycles, and then go on to remark how it can be further refined for certain kinds of groups. What I can prove is the following. Via representation theory, Ratner's theorem holds if U as a unique fixed point in G mod minimal parabolic. It is equivalent to saying that the unipotent group is contained in a unique maximal unipotent group. For such unipotent groups, it will work. For instance, if you take SL2R, there's only one unipotent one-dimensional group. It is more generally, you take a regular element in a regular unipotent in a semi-simple group that has the property. It's contained a unique maximal unipotent group, and therefore it will work. So this is the only case beyond the unipotent radicals of parabolic group, beyond Horner cycles. This is the only case where I have no a proof, unless somebody picks a hole in the proof during this lecture, which is not ruled out. Okay, so back on this. The first thing one has to know is the following. Look at L2 of G mod gamma. This decomposes into a direct sum of irreducible unitary representations into direct orthogonal direct sum. Of irreducible unitary representations of G. This is essentially theorem due to Gelfand. It's more or less it's proved more or less like the Peterwald theorem. It's not really very different, the proof. Okay, L2 G mod gamma decomposes into orthogonal direct sum of irreducible unitary representations. So you start with mu a measure on, so you have L2 G mod gamma. Sorry?
Why does it decompose?
That's a theorem. It decomposes into an orthogonal direct sum of unitary irreducible representation. It's a theorem due to Gelfand. And its proof is easy. It's similar to the proof when you take a compact group. If you look at L2G, it decomposes. The proof in the compact case works almost verbatim for G mod gamma. L2 G mod gamma therefore decomposes into an orthogonal direct sum of V rho unitary irreducible. Let me call it H rho. Now mu is a measure on L2 G mod gamma. Therefore, it is defined on all functions on L2 G mod gamma, which are infinitely differentiable, for instance. And therefore, you can think of it as a distribution as well. And when you think of a distribution, you can talk of its restriction to the C infinity vectors in H rho. Okay. Mu can be restricted to C infinity vectors. In fact, you can restrict it to elements of this which are continuous functions, but in particular, you can do it for C infinity vectors in H rho. Now, these are irreducible representations. I'm looking at C infinity vectors. In fact, I can even restrict to so-called K finite vectors in H rho. That is vectors which transform according to finite dimensional representation under K. If you look at the vector V and look at the action of K, you get an orbit under that and take the span of that. Sorry?
K is the maximal.
I forgot to say that. I have to say what K is. K, a maximal compact subgroup. Okay. And the K finite vectors are automatically C infinity. They are even analytic. And the center acts on K finite vectors through scalars. That's one of the theorems of representation theory. The center of the enveloping algebra acts, because they are C infinity vectors, the enveloping algebra acts on the C infinity vectors, and therefore on K finite vectors. It turns out the center UG is the enveloping algebra of the Lie algebra of G. UG acts on k finite vectors in H row let me call that subspace V row of H row. And the center of UG acts as scalars in V row. Now, if you look at the enveloping algebra, it decomposes as UG can be written as U, say what it is presently, UN plus U centralizer of okay, UM UN minus UN plus where let me fix the notation. P is a maximal parabolic, sorry, minimal parabolic. With Lie algebra P N plus this Lie algebra of the Horner cycle of the unipotent radical of P and M is a Levy supplement to N plus in P and N minus an opposing nilpotent algebra normalized by M. In other words, the G decomposes as N minus plus M plus N plus. Once you have the direct sum decomposition, follows that the enveloping algebra decomposes like this. Now, with that decomposition, it turns out if you look at the center of the enveloping algebra, which I denote ZG, center of UG, take an element Z in ZG, then it turns out Z equals something in the, let me write A plus B, where A is in the enveloping algebra M and B is in the ideal you can write every element in this form, A plus B. Now, suppose mu, I'm looking at, I'll now prove the theorem in the special case when the unipotent radical of a parabolic group, of a minimal parabolic group. The general case is very similar. I will not do it because it gets a little more technical, but the proof is essentially the idea is the same. You look at A, so the element Z equals A plus B, it's like this. Now I know that A plus B, when I apply it to the measure mu, restricted to, when I say restricted to that, I automatically mean I'm restricting it to C-infinity functions in the corresponding space. So let me write A plus B restricted to just V. It's only on V, A plus B is going to make sense. It's going to be A mu. The reason is B kills mu, starts off with UN plus. And I'm assuming that UN plus, the measure is stable, is invariant under the unipotent group. I'm looking at the case of the Horner cycle, as I said. So the group, the notation of, P itself equals M times U. So the Lie algebra of U is N plus for me. The measure being U invariant means infinitesimally N is going to kill, N plus is going to kill. And when I write P like this, so this is the, I shouldn't write UG N plus, not UN plus. N plus kills it. Sorry? A is in UM. Oh, sorry, B is equal to A mu because since B mu is 0. N plus kills mu. B is in UG times N plus, and A is in UM. So B kills it. Start off with N plus. The first thing is N plus, so N plus kills it. So you get A plus B mu is equal to A mu. And A, in fact, in this business, A has a special form. A is going to be in the center of UM. Now, if you look at let H be the maximal split toral algebra inside M, then what happens is this. If you look at H times center of UM, this will be H times this. This is a finite module, finite module over, let me over the center of UM. What I have here is the following. I have this algebra UH times center of UM. This contains UH. What I want to say is that as a module over UH UM, this is a finitely generated module. This, that is, I want to say that UH equals UHGM. Sorry, this is a finite generated module Z of U. So UH is sigma VI other ZUM VI sum I equal to 1 to M. It's actually a finite module over finitely generated module over ZUM. Now ZUM acts as scalars. See, this A, actually, as I said, is in the center of UM, it's in ZUM. A plus B acts as scalars. Z equal to A plus B acts as scalars. B acts as 0. So the whole of everything in, so elements in ZUM, we have elements, let me give it a name. A, we have A mu, chi of A mu, where chi is an algebra homomorphism from UM from Z UM. So A mu is of the form chi A times mu. Now, I know that this is a finite module, which implies every H in H is such that H acting on mu, okay, there is such that there exists a polynomial of degree equal to this number n, p, such that pH is 0. Which implies UH mu is a finite dimensional vector space. So under the action of this H, which is the maximal abelian diagonalizable subalgebra of G, you know that UH mu is a finite dimensional space. This implies, look at the action of H. H has the, UH mu decomposes as a finite sum of generalized eigenspaces. Now, so far, all this does not use the fact that mu is a measure. We've not used it at all so far. It's just that any distribution also, the whole thing will go through. We'll now come to see how to use it as a measure. Now, see, since mu is a measure, we know on the space of probability measures, we have a norm-preserving action. The action of, on this set space, the action of G preserves a norm, preserves some norm. On the space of bounded, on the space of continuous functions, you have the sup norm, which is invariant under left translation. And therefore, the norm on the probability measure is the dual norm, which is also going to be invariant under translations in the group. So these are all these space of measures. The action of G preserves a norm, and hence all. Now, you look at the probability measure restricted to, what I want to say is the following. So on this space, hence, we have, now wait a minute. Once this is finite dimensional, we know get action of H on the space UH mu, which is contained in this. So H on UH mu, well, And that means, when something, you have the action of UH, but then it can be integrated to an action of the group itself. Get action of the group. Maybe I should give it a name of the group. Corresponding to H on UH. And it's clear that if you look at the smallest group corresponding to H, let me call that some script H, because I've used H for something else. So this is so on this space, because it's finite dimensional, we can get action of H itself, because you have finite dimensional representation of the Lie algebra, you can integrate it to a representation of the group. But that obviously must coincide with the original action of the space of probability measures. So now we know on that space the action is non-preserving, which implies eigenvalues of H acting on UH mu, sorry, H acting H in H acting on UH mu are necessarily of modulus 1. Must be, if you have any eigenvalue, it must be multiplication by e power I theta. I should be a little more careful, because I'm restricting, when I look at the measure mu, when I restrict it to the functions which are in the space, which are in the space H rho, and restrict them, the measure may restrict when you restrict it and calculate the norm as the dual of this, the norm may decrease. But that doesn't happen because both H and H inverse are available to us. If one decreases, if one strictly decreases, H inverse will strictly increase. For that reason, it does preserve the norm in any case. So you find that the eigenvalues are necessarily of modulus 1. And there's a little trick involved to actually prove that the eigenvalue is necessarily plus 1. It cannot be something different from 1. And unfortunately, I forgot to bring my notes along with me, and I forget the proof. I can't get it back. Thinking this, I was thinking for the last hour about it, but I couldn't get the proof. But it's quite easy. It's not difficult. There's a little trick involved, and you prove that eigenvalues is actually 1 all the time. And in fact, its eigenspace is a whole space. It doesn't act unipotently, it acts. So action is trivial. Now, yeah. Actually, I want to, from this action is trivial, implies mu restricted to H rho is 0 for every row. Requires a little bit more of work to conclude that. You want to prove the eigenvalue is 1, restrict to that, you find it has to be 0. Mu restrict to that has to be 0. Once again, as I said, this is not difficult, but at the moment I'm not able to recall the proof. So mu which means what? Our measure is such that it is 0 on every one of these H rows. In all this, I have to use the fact that rho is, I'm looking at only rho which is non-trivial, because otherwise the character is that of the trivial character. And that can happen only if the trivial representation is around here. So all that shows us that is 0 if rho is non-trivial. So in this decomposition, the trivial representation occurs exactly once. And if the measure is 0 in all the other orthogonal complements, then it has to be the Haar measure. There's no other choice. That's the proof in the case of the unipotent radicals. Now, what little more? What exactly I can say, which is a little more, is the following. As I said, suppose U is a unipotent group. Subgroup, you can assume without cross generality, it's a subgroup of okay, U is a subgroup of maximal Horner cycle. Which fixes a unique point in G mod P. Suppose that happens. Then look at the restriction of mu to G mod P. I'm sorry. Yeah, here there's one more fact which I have to, one representative theory which I have to use, which is somewhat deep. Namely, it's the theorem of Castleman. It says that any representation, any irreducible, what you call GK module, which is really K finite vectors in an irreducible representation, can be embedded in a principal series representation. So this means you take X, a finite dimensional, irreducible representation of the parabolic minimal of the minimal parabolic, which is trivial, irreducible representation sigma of P, which is trivial on the unipotent radical. And then look at the induced representation from P to G of this sigma. Such a thing is called a principal series representation. And the theorem of Castleman says that anything can be embedded into this induced representation. So in other words, you can think of H, what I call H rho, as sections of a vector bundle on G mod P. Okay. Sections of vector bundle on G mod P. So your space, which I called V rho, can be identified with when I go over, V rho can be identified with K finite sections of the vector bundle on G mod P obtained from sigma. And now, once again, you have this identification. One can see that if you go to C infinity vectors in the whether you think of it as elements of this or elements of that induced representation, they are the same. This involves a little bit of work in the sense that you have to, the Castleman theorem tells you it's a purely algebraic result, but you would like to say that C infinity things here in that representation are actually also same thing as C infinity here. This involves a bit of Sobolev lemma kind of argument. It's not difficult, but it requires something. Now, so you can really think of mu as a distribution on G mod P. It's not a distribution, it's on a vector bundle. It's in the dual of C intersections of vector bundle. So something like a distribution, except that it's not a bundle is not trivial. Now you know that the situation is this. Here is a space, and you have a group U acting on this G mod P, and on a vector bundle on that. And you have your distribution is invariant under the orbits of U. So if you look at the orbits, you can throw out, how do I say this right? If you look at the orbits, if you throw out a closed set, the rest of the thing, open set, factors like this over some space below. And if you have an invariant distribution on this, it is easy to see the distribution really, I mean, you can usual thing of taking disintegrating measures, something similar to that. You find the distribution becomes some parameterized family of distributions along each fiber. And each fiber, it's U invariant. And there's only one U invariant distribution on a fiber. Fiber is of the form U modulo some subgroup. These fibers, after throwing out an open set, it's the same. It's always, fiber looks the same. It's U mod H all the time. And on U mod H, there's only one possible invariant distribution, namely the Harmatian. So it becomes Harmatian along this. And then you have some parameter going through it. But the fact that the G mod P is compact tells you that you cannot have something like that. That the whole thing will have to be therefore concentrated in the complement of these orbits, which means it's in the fixed points. So the entire thing, the entire distribution has its support in the fixed points of the unipotent group, which you see is that under our assumption is a single point. So the entire distribution has support at a single point. Now, if it's at a distribution at a single point, what happens? It's obviously going to be the derivative of the Dirac at that point, basically. I mean, I'm talking as if there's a trivial bundle, but you know, it's a technical problem to adjust to get to sections of vector bundle. So basically, what you find, it's a derivative of Dirac, but and you know, the distribution is automatically, I mean, when I make a distribution, it has to live on all functions with derivatives up to some stage, up to some finite stage. And that means you're looking at a derivatives of Dirac of only a finite number of derivatives and their span, which means it's in a finite dimensional space. Okay. Now, and now on that finite dimensional space, let's look once again at in a situation where we have a say okay, let's, I mean, this again requires a little bit of work. Let's assume that we are in a situation when the normalizer of that unipotent group has an element which is semi-simple. Okay. If you look at a semi-simple element operating on this, an argument very similar to what we have done earlier tells you that this the space is finite dimensional, so you get an action of the one parameter group corresponding to a semi-simple element, and which again preserves some norm. Just transport the norm you have here, coming from bounded from continuous functions to which can restrict to C infinity functions, transport it there. So there's a non-preserving map, which means H has to preserve the measure. So it's a which preserves the measure, and you argue similarly. You look at H and U together, they fix the measure, would mean the entire group will fix the measure, because you can take the U minus part, so to speak, and the group, everything together will fix the measure. And from that, it's not it's reasonably easy to show that the measure is invariant under the whole of G, which means it is a Haar measure. Whole of G, which means it will become zero in all those irreducible components except the trivial component, and therefore it's going to be the Haar measure. That is the, well, this is broadly the idea of the proof. I'm not sure I conveyed things very well, but any attempt to clarify it further will probably confuse you further. So I will not attempt to do that. The main ingredients are to say, you look at the decomposition into spaces and then look at the measure restricted to each of them, each one of them, and then you try to prove it's zero. When it's the full unipotent radical of the parabolic group, it's reasonably easy to conclude that. The crucial point is to the fact that the measure is used in saying that there's a norm on the space which is invariant under the whole group, whole of G. Use that, and essentially the same kind of argument is applied here, except you analyze a little bit more. I'm assuming that there's only one fixed point. If you remove the fixed point, you get an open set in which you will operate, and then you look. What you have to do is you throw out all those points where the orbit is of less than the maximal dimension possible. Then you get a fibration, and you get something U invariant along the fibers, which you show it has to be Haar measure. But if it's Haar measure, it cannot be, it cannot be, it cannot be finite on the whole space. Because it's on each on this open set itself. If you look at the Haar measure, it is infinite. So the homogeneous space of U is necessarily non-compact for this action. The homogeneous space, and if it's non-compact, if you have a Haar measure, the measure becomes infinite. So that cannot hold, because we are talking of a finite measure which gives a distribution. So on the whole, so that's why the measure essentially has to be zero in. That's the kind of proof. That's the kind of argument that is involved. Once again, one uses the fact that it's a measure in that G preserves a norm on the space of continuous functions. Well, okay, that's really all that I have to say by way of proof of this. There are obviously various difficulties. First difficulty is how to remove the condition that there's a unique fixed point. Once again, if you look at the support gets into set of fixed point, that you can immediately prove. But unfortunately, unlike in the Dirac case, unlike when it's a single point, you can say that the measures you get in the orbit of H is finite dimensional. That kind of argument fails, because now you have infinitely many possible derivatives in the direction transverse to the orbits, to the fixed points. So if you take the fixed point set, may be more than a point. It's it'll have manifolds contained in it, and then you can have transversal directions. There are infinitely many transversal directions in which integration is possible. So it becomes a little more complicated. So I've been trying to handle that. So far, I've not succeeded. That's one difficulty. And of course, I mean, that is the difficulty. There's nothing more. How to somehow reduce it to a finite dimensional situation is what one has to see when the fixed point set is not just single element. Well, the other thing, of course, one would like to have is the theorem without the assumption that G mod gamma is compact. Assume that at least G mod gamma is finite measure but not compact. In that case, what do you do? And there are more difficulties because there is no direct sum decomposition, but there's a direct integral decomposition. And so, but very often these what you encounter are really technical difficulties which you can get around very often. But still, I've not been able to do that so far. I've not been able to get around these technical difficulties, but I expect that is not a very serious problem. But once you get around that technical difficulty, then again you can fall back on the other difficulty, which is more serious when the uniform group doesn't have a fixed point. So this is essentially the idea of the proof. My hope is that this proof is worth your while because it connects things with representation theory, and perhaps you can go the other way and say something for representation theory using Ratner's theorem. That's the hope. Well, that's all I want to say.
Questions, comments?
Thank you for your nice proof, but I'm saying, are you passing to k-finite vectors just to use the Castleman thing, or?
Yeah, see, the point is Castleman's theorem talks only about GK modules.
Yeah, exactly.
But one has to make a statement about at the continuous level from the representation to corresponding representation.
Okay.
There, if you take sections of the vector bundle,
Yeah.
which are, say, some number of times differentiable,
Okay.
they will start making sense in the other case also.
Okay.
And then, if with the sublevel lemma, they will become continuous in the other space.
Okay. Okay.
You allow more derivatives here, then you get more derivatives on the other side.
Okay.
Sublevel lemma holds the key to compare the two. So that's why, even though you get a distribution, nevertheless, on the space of C infinity sections.
Yeah.
Even though in the Castleman theorem, it's only from GK module to GK module that you get a injection.
Yeah.
But you can get around that by saying that, okay, you have GK modules that actually is induced by a suitable map.
Okay.
Suitable map at some CK level,
Okay.
some CM level, that kind of thing.
I see. So it's for SL2R, this proof is very easy to see.
Sorry, SL2R?
Yeah.
SL2R, the proof is completely valid because it is uniform radical of parabolic group.
Oh, that is up there. Yeah. Yeah. But
There's no
what would be
difficulty
the
at all.
first case where one would not get in, like checking that?
Sorry?
What would be the case where you check for non-something, higher rank something?
Higher rank, I've already told you what my limitations are. At this point, I cannot go beyond that. But maybe someone younger will have a good idea to push things.
Thank you.